Welcome, learner, to another deep dive. We know you want to get straight to the core of complex topics quickly, but without feeling overwhelmed.
Yeah, absolutely. No wading through dense jargon today.
So today we've got something really interesting, a cutting-edge approach in robot learning that promises exactly that kind of efficiency.
We're looking at a new framework called ReWiND. That's ReWiND.
Right. Rewards without new demonstrations.
Yeah.
The whole idea is teaching robots new tasks just using language, without needing endless examples every single time.
Mm-hmm. Our main source here is the paper Zhang et al., 2025, detailing this ReWiND approach.
And it really does tackle a big bottleneck in robotics. Traditionally, teaching robots is, well, it's a slog, isn't it?
Oh, definitely. You either need massive data sets of demonstrations or you need experts to sit down and painstakingly design these reward functions. Very time-consuming.
So our mission today is pretty clear. Figure out how ReWiND works its magic, why it's such a big deal, and maybe what surprising things it might enable for robots, like in our homes or workplaces.
Sounds good. Where should we start? The challenges.
Yeah, let's set the stage. What exactly were those traditional methods struggling with?
Okay, so you've got imitation learning, the robot watches and copies. Sounds simple, right?
Sounds intuitive.
But the catch is, you need so many demonstrations for every single little task variation. It's just hugely expensive and slow. Imagine showing a robot how to open 10 different types of jars, hundreds of times each.
Ugh, yeah, impractical for scaling up.
And the other way, reinforcement learning.
Right. RL. The robot learns by trial and error, guided by a reward signal, like getting points for doing the right thing.
Okay.
But designing that reward signal, that's the tricky part. It takes serious expertise. Get it wrong,
Yeah.
and the robot learns weird shortcuts or just, well, fails.
So you need an expert engineer tweaking things constantly.
Pretty much. And that led people to think, well, maybe language could help guide the reward.
Makes sense. Use instructions to shape the learning.
Yeah.
But that had its own issues. It did. Early attempts often needed things you just don't have in the real world, like perfect knowledge of the robot's state or still thousands of demonstrations or needing to train the reward system all over again online for each task.
Right. Not quite ready for prime time. So this is where ReWiND comes in. What's its big idea?
The core concept is pretty clever. ReWiND learns both a language condition reward function, so how to judge progress based on instructions, and a language condition policy, how to act based on instructions, all from a, well, surprisingly small initial set of demonstrations.
Small how?
We're talking like maybe 5 examples per task in that first batch.
Wait, 5? Just 5 examples per task. That's tiny compared to what you were saying before.
Exactly. That's the efficiency leap.
So how does it go from just 5 examples of, say, picking up a block to understanding a new instruction like slide the cup left?
It's a 2-stage process. First, there's pre-training. It uses that small initial data set to learn the general reward function and a basic policy. Think of it as learning the fundamentals.
Okay, building a foundation.
Then, stage 2, fine-tuning. You give it a new task just using language. The pre-trained policy starts trying things, and the pre-trained reward function gives it feedback based on that language instruction. And this happens with minimal extra interaction with the world.
So it learns the general connection between language, actions, and rewards first, and then applies that understanding to new situations. That's smart. Let's dig into that reward model. How does it actually work? How does it give useful feedback and generalize?
Yeah, the reward model is really key. It's designed to do 3 main things: give dense feedback, generalize to unseen tasks, and be robust, handle different robot behaviors.
Dense feedback. What does that mean exactly?
It means instead of just getting a single reward at the very end, like task complete or failed,
Oh.
the model is constantly evaluating how much progress the robot is making during the task, frame by frame, based on the video.
So it's getting continuous guidance, like getting warmer, getting colder.
Precisely. It predicts progress within the demonstration videos, which gives a really rich signal for learning.
That makes a lot of sense for learning faster. Okay, and what's this video rewinding thing? Sounds intriguing.
Yeah, it's a really neat trick. So you have a video of the robot successfully doing something, like picking up a cup.
Right.
Video rewinding takes a segment of that success, maybe right after the grasp, and just plays it backward.
Plays it backwards so it looks like.
It looks like the robot is dropping the cup or failing the task in some way.
Whoa. So you can generate failure examples automatically just from successful ones.
Exactly. You don't need separate failure demonstrations. The reward model learns to give negative rewards for these rewound failure-like sequences. It learns what not to do, basically for free, data-wise.
That is incredibly clever. Talk about data efficiency. Okay, so it gives dense feedback, learns from failures via rewinding. How does it generalize so well to tasks it's never seen?
A big part of that is the data it's pre-trained on. ReWiND uses the OpenX dataset. It's huge. About 356,000 robot trajectories, nearly 60,000 unique task descriptions.
Okay, massive variety.
Yeah, things like pick Coke can from fridge, drag the circle left of the star, all sorts of stuff. This broad exposure is crucial.
And it uses pre-trained AI models too, right? For vision and language.
It does. It leverages powerful models that already understand a lot about images and text. Specifically, Dino V2 for vision, good at object-centric stuff, and all minimum for language processing.
And these are kept frozen. Why is that important?
Good question. Since the initial demonstration dataset for ReWiND itself is small, freezing these powerful pre-trained models prevents the system from forgetting all the general knowledge they have and just overfitting to the few examples it sees.
Ah, okay. So it forces ReWiND to build upon that existing knowledge rather than potentially messing it up with limited data.
Exactly. It encourages generalization. Then ReWiND uses its own lightweight component, a cross-modal sequential aggregator, basically a small transformer,
Right.
to combine the information from the frozen vision model, the frozen language model, and the video sequence over time to actually predict the reward.
So it learns to connect the visual scene, the language instruction, and the robot's actions. And there was something about positional information, preventing cheating.
Yes, another subtle point. To understand the video, you need sequence information. But if you tag every frame with its exact time, the model might just learn to associate reward with, say, the last few frames, without understanding why those frames represent success.
Okay.
So ReWiND only adds positional info to the very first frame. It forces the model to pay attention to the actual content of the actions unfolding, not just the timestamp.
Smart. Okay. One more piece of the reward puzzle. Handling different ways of saying the same thing, like take out the trash versus dispose of the garbage.
Right. For that, they use a large language model, an LLM, during the data preparation phase. For each task in their small initial data set, they use the LLM to generate like 5 or 10 different ways to phrase the instruction.
Ah, automatic paraphrasing.
Yep. Dispose trash, throw away garbage, put waste in can. Training on these variations makes the final reward model much more robust to how a person might actually talk to the robot.
Okay, so that's the reward model. Dense feedback, learning from failure via rewinding, generalization through big data and frozen embeddings, and robustness via instruction augmentation. Really sophisticated. Now, how does the robot actually learn to act using these rewards?
That's the policy learning part, also in 2 stages, mirroring the reward learning. First, pre-training.
Okay.
The policy, the robot's action decision part, is pre-trained using offline reinforcement learning.
Right.
It learns from that initial small set of demonstrations. And crucially, the reward signal for this pre-training comes directly from the ReWiND reward function we just discussed.
So the reward function it just learned is immediately used to teach the initial policy.
Exactly. They also add a little bonus reward for reaching the final goal in the demonstrations, just to give it an extra nudge towards success.
So it learns a basic way to behave that aligns with the language-aware reward function, and then the second stage, when it sees a totally new instruction.
Right. For a new task specified only by language, that pre-trained policy is then fine-tuned online. It interacts with the environment, tries things out.
Mm-hmm.
And the ReWiND reward model provides the reward signal, telling it how well its current actions match the new language goal.
Mm.
There might also be a simple success signal, maybe from a person confirming, yes, you did it, which can provide another reward boost.
This whole process sounds incredibly efficient. Learn general principles offline from a few examples, then quickly adapt online using that learned reward model. It seems almost too good to be true. Did it actually, work? What did the experiments show?
Yeah, the crucial question. The experiments were designed to test 3 main things. One, is the ReWiND reward function actually good? Does it correlate with real progress?
Okay.
2, can this system actually train policies to do new unseen tasks effectively?
That makes sense.
And 3, which bits of the ReWiND design, the rewinding, the augmentation, etc., really matter most?
Got it. So question 1, how good was the reward function itself compared to others?
They used the MetaWorld benchmark, a
Yeah.
standard simulation environment. They compared ReWiND to other methods like Levy, RoboCili, VLC, GVL. ReWiND came out looking really good. For instance, they look at confusion matrices, trying to match unseen task videos with the right language instruction. ReWind's matrix was much more diagonal heavy. meaning it was much better at correctly matching the video of task A with the instruction for task A, task B video with task B instruction, and so on, even for tasks it hadn't seen before. High accuracy in understanding the link between action and language.
Strong sign of generalization. What else?
The measured correlation. How well does the predicted reward track actual progress in successful demos? ReWiND showed significantly higher correlations Pearson's R, Spearman's RU than the others. Its rewards really mirrored what was happening.
Okay, so it understands success well. What about failures or partial success during learning?
This is where that video rewinding really shone. They tested if the reward models could correctly rank rollouts, like a clear failure should get a lower reward than a near success, which should get less than a full success. ReWiND was way better at this, distinguishing between failure, near success, and success. The paper mentions something like a 74% relative improvement over the next best method in getting this ranking right. That rewinding trick seems key for providing informative feedback during learning.
Huge improvement. That suggests a much more useful signal for the policy and robustness to different phrasing.
Also strong. ReWiND had the highest average correlation across different phrasings of the same instruction and very low variance. So whether you said dispose trash or put waste in can, it understood and gave consistent rewards. That instruction augmentation clearly worked.
Okay, so the reward function seems genuinely powerful and robust. That leads to question 2. Does this translate into actually learning new tasks?
Yes. In the MetaWorld simulation, they tested learning completely unseen tasks after 100,000 steps of online fine-tuning.
Which is not a huge amount in RL terms.
Right. Relatively little interaction. ReWiND achieved an average success rate, the IQM score of 79% across these new tasks.
79%. How did that compare?
It was almost double the success rate of the best baseline method in their comparison. A really significant jump in learning efficiency for novel tasks.
Wow, okay. That's impressive in simulation, but the real test is...
The real world. Exactly. And they did test it on a physical two-armed robot.
A bimanual Koch arm, I think the paper said?
That's the one. They took a pre-trained policy and fine-tuned it for just 1 hour using ReWiND rewards online.
1 hour. Okay. And the result?
A 5-fold increase in success rate across a diverse set of challenging unseen tasks. These included tasks with visual clutter, tasks requiring new spatial reasoning, even tasks with novel language phrasing.
5 times better on a real robot in just an hour. That's genuinely practical. That feels like it could actually be deployed.
It's a very promising result for real-world application, definitely. It also significantly outperformed the best simulation baseline when tested in the real world.
And briefly, the third question, about which parts of ReWiND mattered most?
Yeah, the ablation study confirmed the importance of the key ingredients, taking away things like the target environment data, the OpenX data, the video rewinding, or the instruction generation. Each of these hurt performance noticeably.
So it's not just one magic bullet, it's the combination of these clever ideas working together.
Exactly. They all contribute meaningfully.
Okay, this sounds incredibly promising, but like all research, I assume there are limitations or next steps?
Oh, absolutely. The researchers are upfront about that. One thing is that ReWiND still relies a bit on the initial pre-trained policy, being decent enough to explore effectively during the online fine-tuning.
If it starts out totally clueless, it might struggle to find the rewards.
Potentially, yeah. Also, the frozen embeddings, while great for generalizing from small data, might be a limitation for highly specific tasks that weren't well represented in the original vision language model training. They mentioned an example with diff scrubbing where it wasn't perfect.
Right, the trade-off between general knowledge and task-specific nuance.
And currently, the experiments still need a human to reset the environment between tries.
Okay.
And they need some way to know if the task was ultimately successful for that final bonus reward. Automating those aspects is important for full autonomy.
Makes sense. So what's next? Where could this research go?
They suggest several interesting directions. Combining ReWiND with even better policy learning algorithms, maybe finding ways to carefully fine-tune the input embeddings with more robot-specific data, exploring reset-free RL methods so the robot can learn continuously.
Right. No human resets needed.
And potentially using advanced vision language models, VLMs, to automatically detect task success instead of needing a separate signal.
Lots of potential to build on this foundation. Okay, let's try and wrap this up. What's the core takeaway for you, learner, from this deep dive into ReWiND?
I think the main message is that this is a really significant leap in making robot learning more efficient and practical. ReWiND shows it's possible for robots to learn new skills effectively just from language guidance, using only a small initial batch of demonstrations.
Yeah, the efficiency is key. It moves away from needing massive data sets or complex manual reward engineering. It feels like a genuine shortcut to more capable robots.
It does, and that efficiency, that ability to learn from language, really opens up some thought-provoking possibilities, doesn't it?
Absolutely. And maybe that's the final thought for you, learner. If robots could learn new skills just by us telling them what to do, maybe refining it a bit through interaction, how would that change things?
Yeah, think about how we interact with robots day to day. What tasks around your home or workplace could you imagine teaching a robot just using language if this kind of technology matures?
It really shifts the perspective on human-robot collaboration. It's an exciting glimpse into a future where teaching robots might become much more intuitive and accessible.
Definitely a space to watch. Language-guided learning seems poised to make a big impact.
Well, this has been fascinating. Hopefully, this deep dive into ReWiND has given you a clear picture of this innovative approach and sparked some ideas about what's coming next in robotics. Thanks for joining us, learner.
Yeah, thanks for tuning in. We'll catch you on the next deep dive.